Hello and welcome to the lesson on electric potential energy. So what is today's goal? Today's goal is I can explain the concept of electric potential and calculate associated values that arise in real-world applications. So what are we looking at or we're starting with today? Well, we are going to do a bit of a walk down memory lane here for 1 second. And we're going to talk about Newton's gravitational formulas. So Fg equals G m over r squared. We know that G is equal to Gm over r squared. And I compared these yesterday, and that's why I want to start on them today, because it produces or creates a pattern. Q1, Q2 over r squared, and our electric field strength is the KQ over r squared. So electric potential is very, very similar to gravitational potential. Gravitational potential energy, if you recall, was G m over r. So you can kind of anticipate what our formula is going to look like then with its counterpart, because each one ends up being somewhat related. So as we move through then here, electric potential energy, what is electric potential energy? It's the energy stored in a system of two charged particles a distance of r apart. So two particles that are separated, if you're holding them in place and they want to move, you are storing potential energy. So that formula, most of you hopefully have predicted, KQQ divided by R. All right, so that is the particle energy. So the energy contained between two particles at a distance r being held in place. All right, they want to move. They want to convert that energy to kinetic energy. They want to go, and they can't because they're being held in place there. So, sign convention, they can be positive or negative, so it depends on the charges. So depending on charges here, can be positive or negative. So it kind of depends on the situation and the orientation and your convention. So we will talk about that when we get to some of the word problems. So similar to gravitational potential energy, if we look at it kind of graphically, so this is stored energy. As the distances move apart, the amount of energy decreases. So the green situation I just drew would be if we were looking at Q1, Q2 being a positive charge. So if the two particles were positively charged, you'd have positive energy, and you would, as you moved away, the further and further they are apart, the less and less they're pushing on each other. Similarly, if we had particles on the other side, it would produce what we call negative energy. So Q1, Q2, we're looking at a situation where they are what we consider negative energy or opposite charges. Opposite charges, whereas this one would be for same charges. All right, so same as gravitational, you get less and less effects due to gravity the farther you move away from the planet. Similarly here, as you move the particles further and further away, you get that asymptotic relationship where the energy is decreasing but never reaches zero because it kind of handles that infinite distance, I guess you'd think of it that way. So off we go then. Back to electric potential. We know from our 3U review that electric potential is also known as voltage. So now I've dropped the energy, you'll notice it's just electric potential. And that is what we associated with voltage all the time. So electric potential looks at the positive unit charge, Q2, when it is in a field, in any field of another charge, which we'll call Q1. So if you remember from our review, voltage is the energy divided by our charge, Q. So V equals E divided by Q. Well, what is the formula for energy? So I'm just going to do a bit of a replacement here. Well, energy is just K Q1 Q2 divided by R squared, and that would all be divided by Q. All right, now that Q then is going to be Q2, because we're talking about, right here, we're talking about positive unit charge in any field. So it's entering Q1's field. So that's what we're interested or focusing on is Q1's effect. And the Q2s would then end up canceling or dividing out, leaving me with an equation for voltage of K Q1 over the distance R. So there is a formula you'll want to add in to that cheat sheet, and that is your electric potential or the voltage as we learned to know it in the grade 11 course. So very important that we can distinguish between the two, all right, because they're very, very similar. Electric potential energy of a charge at a point, and V is the electric potential at a point. So they're very similar. They're only separated by that single word in terms of terminology. So trying to clarify that. The concept of electric potential energy, so I'm referring to EE, can be extended to include the electric field that results from a distribution of electrical charge rather than just a single point charge. So remember, electric potential is the work it takes. So electric potential is voltage. It's the amount it takes to move a charge from point A to point B. So from one point to another. So in this particular case, we're dealing with a difference in electric potential. So the difference between 2 points. So I have this nice little diagram here. So electric potential difference is the amount of work it takes for us to move the particle from point B down to point A. And it doesn't matter the pathway that you choose. So for example, we could take a direct route from one to the next. So you look at it as that being the pathway. So we move from point B to point A in that fashion, or it could be that pathway, or it could be also that pathway as well. All right, so it doesn't really matter which pathway we choose. We're looking at the difference between point A and point B. So delta V1 will equal delta V2. Okay, in terms of our pathway, I guess, and I have a third one there, which would equal delta V3. So those match up with pathway 1, pathway 2, pathway 3. So those are my 3 pathways. So I just want to draw a quick comparison here. So I'm going to extend my page a little bit and add in a bit of a note then. So it's always the tricky part for you as the student to differentiate between the two. So EE is the energy involved when 2 charged particles have their fields interact. All right. So their fields interacting. So if we had a charged particle, and here's its field, and create another one right here. If we were to move my second charged particle closer, right in here, so that area where the fields are interacting, okay, is where that energy is coming from or emanating. All right, so move particle away, fields interact. Okay, so it's that region in there that's causing that energy created. Now V is the energy required to move a particle from point B to A. All right. So we're looking at moving it from point to B to A, and we talked about the pathway doesn't really matter here. All right. So that allows us or leads us into our next slide then. So looks like I just put it in the slot, or so I had the slide already made up for you and where to put all that information in. So I do apologize. So hopefully you looked ahead and saw that. So let's look at some formulas. This is where it gets a little bit messy just in the arrangement here. So we're looking at electric potential difference. So by definition, two positively charged plates. Okay, so I'm looking at, oh, my mistake here. I got to clean up my formatting isn't quite right here. Just a sec. There we go. So electric potential difference. So by definition, we are looking at the difference in energy. So delta E here is equal to EE2 minus EE1. So the difference in locations. So using our formula, we have QV2 minus QV1. So Q is our charge, V is our voltage, and our electric field is Fe divided by Q. We rearrange it. Fe force is equal to our electric field strength times Q. And I realized that this spacing, no wonder this doesn't make any sense. I'm gonna just edit this and we'll go into the next video and we'll start fresh because hopefully your printout is correct because my smartboard sheet is highly incorrect. I was wondering what was going on with that. Sorry about that. We'll see you in the next video with it, my slides cleaned up.